Recurrent neural networks have a frustrating property. When you scale them up, they should get more expressive and more powerful, but in practice, they tend to overfit so badly that practitioners are forced to use smaller models than the task really deserves. Meanwhile, on the feed-forward side of the deep learning world, there is a beautifully simple regularization trick called Dropout that has become standard equipment. You randomly zero out a fraction of the activations during training, which forces the network to spread its bets across many features rather than relying on any single one, and the result is dramatically better generalization. The puzzle this paper tackles is why that same trick, when applied naively to recurrent networks, fails to help, and how to fix it. To understand the problem, you have to think about what makes recurrent networks special. A feed-forward network passes information through a fixed number of layers in one shot. A recurrent network, especially the long short-term memory variant, or LSTM, is designed to carry information across time. The whole point of an LSTM is that it has a memory cell that can hold on to a piece of information for many time steps, deciding at each step whether to override it, read from it, or preserve it. This is what lets these models handle language, where the meaning of a word can depend on something said many words earlier. Now imagine you apply standard dropout to every connection in this network, including the connections that pass the memory state from one time step to the next. Every time the memory tries to travel forward in time, it gets randomly corrupted. If your sequence is 50 steps long, the signal has been blasted with noise 50 times. Earlier work by Bayer and colleagues observed exactly this and concluded that dropout and recurrence simply do not mix, because the recurrence amplifies the noise. The fix proposed here is almost embarrassingly simple, but the reasoning behind it is what makes it work. The authors apply dropout only to the non-recurrent connections, meaning the connections that go from one layer up to the next within a single time step, and they leave the recurrent connections, the ones carrying memory through time, completely untouched. Picture the network as a grid where time runs horizontally and depth runs vertically. Dropout is applied to the vertical arrows, but not the horizontal ones. The consequence is that any piece of information traveling from an early time step to a later prediction passes through the dropout operator a number of times equal to the depth of the network plus 1, regardless of how far it travels in time. The corruption is bounded by depth rather than by sequence length. The memory cell remains a clean, reliable highway for long-range information, while the layer-to-layer computations still get the robustness benefits of dropout, forcing them to be redundant and less brittle. Concretely, when the LSTM computes its input, forget, output, and candidate gates at each time step, those computations take in two things: the hidden state from the layer below at the current time step, and the hidden state from the same layer at the previous time step. The authors apply dropout to the first input, the one coming from below, and leave the second input, the one coming from the past, alone. The memory cell update and the hidden state update themselves are completely unmodified. That is the entire recipe. The experimental results are striking precisely because the change is so minimal. On the Penn Treebank language modeling benchmark, an unregularized LSTM reaches a test perplexity of about 114. A medium regularized LSTM with 650 units per layer and 50% dropout on the non-recurrent connections drops that to about 83. A large regularized model with 1500 units per layer and 65% dropout pushes it down to about 78. Ensembling 38 of these large regularized models gets to about 69, which at the time was competitive with the best-known systems that involved much more elaborate machinery. The pattern holds across domains. On an Icelandic speech recognition dataset, dropout improves validation frame accuracy even though training accuracy drops, which is the classic signature of a regularizer doing its job. On English to French machine translation using the sequence-to-sequence formulation, Dropout improves the BLAU score from about 26 to 29. On image caption generation with the MES-GOCO dataset, Dropout produces a single model roughly as good as a 10-model ensemble of unregularized networks, which is a remarkable efficiency win. There are some honest limitations worth surfacing. The method does not let the recurrent connections themselves benefit from regularization, so if the dominant source of overfitting lies in the recurrent dynamics rather than in the layer-to-layer transformations, this approach will not help much. The technique also requires fairly aggressive dropout rates, 50 to 65% in the language modeling experiments, and these were tuned per task. The translation results, while better than the unregularized baseline, still fell short of a strong phrase-based statistical machine translation system from the era. And it is worth noting that a paper by Pham and colleagues independently discovered essentially the same trick around the same time, which suggests the idea was in the air. The deeper conceptual question of how to also regularize the recurrent connections themselves remained open and motivated a lot of follow-up work on things like variational dropout and zoneout. The broader implication is that scaling up recurrent networks no longer requires accepting massive overfitting as the price of capacity. Practitioners could now train LSTMs with hundreds of millions of parameters on relatively modest datasets and get the generalization benefits without losing the model's ability to remember things across long sequences. That unlocked a wave of progress in sequence modeling that carried through the next several years until attention-based architectures eventually took over. Now let's walk through some questions you might have after hearing all of this. Why exactly does corrupting the recurrent connection hurt so much more than corrupting the layer-to-layer connections? The recurrent connection is the only path along which information from the distant past can reach the current prediction. If you noise it at every time step, then by the time a signal has traveled 50 steps, it has been multiplied by random masks 50 times, which essentially destroys it. The layer-to-layer connections, by contrast, are traversed a fixed small number of times regardless of sequence length. So the noise stays bounded and acts as healthy regularization rather than catastrophic signal loss. Could you achieve the same effect by just using a much smaller dropout rate on the recurrent connections? In principle, yes, and later work explored exactly this direction with carefully designed variational schemes that use the same dropout mask across all time steps to avoid the compounding noise problem. But with the naive approach of independent dropout masks at every step, even small rates compound exponentially over long sequences, so you essentially have to choose between zero dropout on the recurrent path or accepting severe degradation of long-range memory. If the trick is this simple, why did it take so long for the field to figure out? Part of the answer is that the conventional wisdom from the Bayer paper had crystallized into a belief that dropout and recurrence were fundamentally incompatible. Once you accept that framing, you stop looking for a fix. The insight here was to ask not whether dropout works with recurrence, but where in the architecture it should be applied, which required separating the recurrent connections from the rest of the computation in your mental model of the network. For large-scale recommendation systems, the lessons here transfer in a direct and useful way. Sequential user modeling, where you embed a user's history of clicks, purchases, or watches into a representation that drives downstream ranking and retrieval, often uses recurrent or transformer-based encoders that face exactly the overfitting tension described in this paper. Users with long histories are precisely the high-value users you most want to model well, and a regularization scheme that corrupts intermediate representations while preserving the integrity of long-range temporal signal is highly relevant. The specific recipe of applying dropout to the vertical layer-to-layer paths, but leaving the horizontal time-traveling memory clean maps cleanly onto deep sequential recommenders. where you want noise to encourage feature redundancy without disrupting the user's coherent trajectory of intent. More practically, the broader insight that ensembling can sometimes be replaced by aggressive regularization on a single larger model has real production value. Serving an ensemble of 10 ranking models at billion user scale is expensive in both latency and compute. But if a single well-regularized model can match ensemble quality, as the image captioning result suggests, you get the quality wins without the serving cost. That kind of single model matches ensemble outcome is exactly the trade you want to make when every millisecond and every GPU hour at inference time has a real dollar cost.